So, we are discussing about the rotation of a molecule, means rotational spectroscopy, so that we can tell about the microwave spectra. So, what we should do, as we have seen that there are different kind of molecules. Okay. One is linear molecule. In respect of rotation, this division is very important. So, one is linear molecule, where I y equal to I z and I x equal to 0, and then your other polyatomic molecules, where some of them are symmetrically top molecule or spherically top molecule or asymmetric top molecules. Okay. So, that I have defined, I have differentiated with respect to moment of inertia, principal moment of inertia. So, so basically we will study here mainly, because this is the simplest one, simpler one, this diatomic molecule, rotation of a diatomic molecule, diatomic molecule. Okay. So, diatomic molecule, so which will give you rotational spectra. And of course, it is in its spectra, it is in microwave. So, it is also called microwave spectra. This is common for all molecules, all rotational molecules. So, microwave spectra, right. So, that is what we would like to see, what is the origin of these spectral lines, of this spectra, of this radiation. Okay. So, for that we have to study this, we have to study the rotation of the molecules, and simplest molecule as I have chosen, that is the diatomic molecule, because it has only one moment of inertia. So you take a problem now. So, we have to use quantum mechanics, we have to solve, we have to find out the energy of the rotational diatomic molecule. Okay, energy of the rotational diatomic molecule, or energy of, or rotational energy of diatomic molecule. So, we have to consider the rotation of the of two body system, two mass system, right. So, in general just consider two mass. Consider these two mass having different mass. So, one is M1 and another is M2, right, and their separation is say it's the separation is R0, say R0, that is the basically bond length. And now for this two body system, let us reduce it to a one body system. So, that is, you know how to do that. So, one has to find out the reduced mass. Okay. So, then it will be converted to the one body system. So, for that one has to consider center of gravity. Okay. So, from center of gravity the distance, so this distance say r2 and this distance say r1, right. So, now you know this, just put r0 equal to r1 plus r2, okay, and then m1 r1 equal to m2 r2. So, that is the this r1 r2 distance of the mass from the center of gravity. Okay. Now, you have these two, r0 equal to r1 plus r2 and m1 r1 equal to m2 r2, right. So, from these two one can yes, and also I know that this I, moment of inertia, in this case linear. So, this is the x axis, this is the x axis, this is the x axis. So, basically Ix equal to 0 and Iy equal to Iz equal to, I have written I. So, I equal to is basically moment of inertia with so this the Iy axis and this other one, this perpendicular to this Iz axis. So, it can be either y direction or the with respect to y direction or z direction. So, both are I think the same. So, just so I will be moment of inertia with respect to this axis passing through the center of gravity. So, distance is r1 r2. So, moment of inertia will be basically m1 r1 square plus m2 r2 square, right. So, these things, so here I can write I equal to m1 r1 square plus m2 r2 square, right. So, from these three relation you can, I will not just derive, but it is you can just easily I think I can show you, let me do it. M1 r1 equal to m2 r2. So, r2 I can replace r0 minus r1. So, m2 r0 minus r1. Okay. So, from here what you will get? So, m1 r1 here m2 r0 minus m2 r1. So, m2 r1 if I take this side, so then I will get m2 r0 equal to m1 plus m2 into r1, okay, equal to by r1. So, here r1 what I am getting, r1 equal to m2 by m1 plus m2, okay. Similarly, just from here itself you replace r1 by r0 minus r2. So, you can show that it will be m1 by m1 plus m2, right. So, I equal to m1. So, now r1 square, if we take this, so m1 r1 square means m2 square. So, I think I will here itself I can write. So, your I will be, so here I am getting m1 m2 square and divide by m1 plus m2 square, fine, plus m2 I am getting r2 m1 square divide by m1 plus m2 square. So, m1 plus m2 square in both cases, and m1 m2 I can take common, then there will be m1 plus m2. Okay. So basically the square will go. So it is a m1 m2 m1 plus m2, and for all cases, so I0 I have not written, so there will be R0, there will be R0 in both cases. So the square of this means R0 square will come, R0 square will come here. Okay. So here this we can write I equal to mu R0 square. So mu is the reduced mass, so mu equal to basically you have m1 m2 divided by m1 plus m2. Okay. Now as if we have one body problem, so we have mass mu. Now its moment of inertia, this mass is rotating with respect to yes. So as if I take this center, so I have another mass, so mass mu. So this mass with respect to it is rotating, okay, and this length is R0. So now it is reduced to one body problem. Okay. So basically you have now a problem like that, like this. So I have basically I have reduced this two body problem to one body problem. So two body problem is now reduced to one body problem, right? So now this is our system. Now this you see this, it's just like hydrogen, how to solve this kind of problem that we have seen, as if this hydrogen like atom. So there basically nuclear mass and electron mass, and we have taken their reduced mass. Okay. So now this is the same kind of problem. Okay. Only difference is that in case of hydrogen like atom, there was a central potential. Okay. So Vr equal to minus Jd square by R, and now in this case this Vr is basically 0. So there is no potential energy. Okay. Only kinetic energy, rotational kinetic energy. Okay. So one can use Schrodinger equation and solve it in same way, and now imagine there. So R0 in this case, it is how to consider this one. Yes. So I think this I have to here I have not told you. So one thing I have to tell that this now when it is molecule is rotating, now this there are two model, one is called rigid rotator, one is called rigid rotator. So this basically there are two model for calculation of this or solving the Schrodinger equation. One is called rigid rotator, okay, and another model is called non-rigid rotator, What is this? So rigid rotator. So you have molecule okay, having the bond length is r0. Now, if this distance is remains same all the time, it's these two atoms are tightly bound with each other. So, there this bond length does not change during rotation. Okay. So, then it is called rigid rotator. It is called rigid rotator, but there are some molecules or most of the molecules basically it is not that rigid. So, during rotation its bond length also changes. So, then it is called non-rigid rotator. Okay. So, this non-rigid rotator is basically it is the realistic model. Non-rigid rotator is not basically not realistic, but for the simpler calculation, let us first consider this rigid rotator, and then later on we will see what effect due to the change of bond length or when it will be the non-rigid rotator. So, what will be the additional effect we will see. So, that we will discuss later on. So, now let us take it is a rigid rotator. So, when it is rigid rotator, so basically r0 this length it will not change, right. In case of hydrogen atom, so r was variable and theta phi. So, psi, so this wave function psi is basically function of r theta phi. So, in this case, in case of rigid rotator, so this r is basically r0, it is constant. Okay. So, this what was the psi r theta phi? So, it was basically r function also. In hydrogen like atom we have seen theta phi, right. It is a spherical harmonics, theta and phi dependent, and this one part is radial dependent. So, in this case this r equal to r0, it is constant. Okay. So, basically there will not be change of this one. Okay. So, only so this the right wave function. This can be the also wave function, but it is the active one. It is this will take participate in the yeah. So, this part is active. Okay. So, basically so this is nothing but that what is the solution for this kind of wave function. So, there here in this case this H Hamiltonian H. So, always Schrodinger equation H psi equal to E psi. So, one has to find out proper psi eigen function, and then for that, for your system you have to write your this Hamiltonian. So, our Hamiltonian will be only kinetic energy h cos square by 2. Now, here you see I will not write 2m, right, because I have already told in case of rotation mass is not important, important is basically I. So, here I will write I h cos square by 2I in place wherever mass will be there I will replace by I. Okay. So, h cos square by 2I. Okay. So, that will be the our Hamiltonian plus your V r term. So, that is basically 0. Okay. So, if you apply this Hamiltonian on this, so this basically it will. So, this one can show this is kinetic energy. It is basically kinetic energy rotational. It's the angular. So, this energy comes due to the angular motion. It's a rotation motion is nothing but the angular motion. So, one can show that this energy is kinetic energy is basically it's due to the angular momentum it comes from the angular momentum, not linear momentum. Okay. So, what about the thing? So, if you solve this Schrodinger equation, so I will not go into details. So, if you solve this equation, and you will get basically this type of result. Here I am showing you. So, solving Schrodinger equation, one can get the allowed energy of the rigid diatomic molecule. So, Ej equal to h cross squared by 2I j plus 1. Okay. So, it is similar to L plus 1, right. So, angular momentum. So, in this case, so energy expression you will get for this rigid rotator solving the Schrodinger equation, this energy expression you will get this. Okay. So, where J is basically here, it is called the rotational quantum number. So, it is equivalent to L basically. So, if this is the energy, so now in terms of wave number I want to write this energy. So, in terms of wave number, so E equal to h nu, nu is c by lambda. Okay. So, hc 1 by lambda. So, I have written here energy. It is not energy, it is basically wave number. In place of nu bar, I have written E small. E in different letters, different form. Okay. HCE, I will tell it is E, but you can say this. There is a just both are E, but we have written in different what is called this different font basically. Okay. So, this E is basically the wave number. E is in terms of wave number of energy level. Okay. Energy level is expressed in place of just electron volt or joule. Okay. We have expressed in terms of centimeter inverse. Okay, energy level. So, that is expressed by E, and nu I have generally nu bar is used. So, nu bar I have avoided because to avoid the confusion. So, nu bar will use the energy of the spectral line. So, basically two energy level whatever the transition, two energy level whatever the transition. Okay. So, that transition, due to that transition I will get the I will get the spectra, okay, or radiation. That radiation will have the frequency or energy. So, that will express in terms of wave number, and there we will use nu bar. Okay. So, that is basically energy of the spectral line. Nu bar will be used to express the energy of the spectral lines, and here E, this E is used to express the energy level in wave number. Okay. So, if so E equal to Hc E. So, this I can write Ej equal to Ej by Hc, okay, equal to h cross square means h square plus 4 pi square, 2 is there, 8 pi square Ic, okay, divide by Hc means it is h square and this divide by h. So, it is h by 8 pi square Ic j plus 1. So, this is the energy level in terms in centimeter inverse. Okay. So, this B, so we have written here B. So, B is nothing but a constant, you see here all are constant for a particular molecule. So, this B is equal to h by h 8 pi square Ic. So, it contains I, okay, moment of inertia. So, now this spectral lines when you will get due to the transition between two energy levels. So, so what will be the energy of the spectral lines? So, that we expressed in terms of nu bar. Okay, nu bar equal to nu bar. So, this nu bar due to transition from j to j plus 1 or j plus 1 to j between these successive two energy levels. So, that is basically, so this energy level, that energy in terms of wave number. So, b j j plus 1. So, I can write j, I can replace by j plus 1. So, it will be b j plus 1 j plus 2 minus j equal to j. So, b j j plus 1. So, it is giving 2 b j plus 1. So, this is the energy of the spectral lines in centimeter inverse or in terms of wave number. Okay. And this b is called basically rotational constant. So, here nicely we got the this energy of the or wave number of the spectral lines of rotational spectra. So, if I plot it, so E j equal to b j j plus 1. Now, just if I draw the energy levels, okay, in centimeter of inverse of course. So, j equal to 0. So, this is the 0 energy. J equal to 1. So, it will be j j plus 1, it will be 2. So, 2 b. So, this 2 b, then j equal to 6 b, 12 b, 20 b. So, that is the energy level in terms of centimeter inverse. Here in terms of b we have shown. Now, when there will be transitions, that selection rule is similar to that angular momentum selection rule, del L equal to plus minus 1. So, here same selection rule is valid, del j equal to plus minus 1. So, if so, del j equal to plus minus 1. So, from 0 level j equal to 0 to j equal to 1, this transition is possible, or 1 to 0, that also possible. So, 0 to 2, 0 to 3, 0 to 4, it is not allowed. So, this transition it will give one spectral line. So, next 1 to 2, 2 to 3, 3 to 4. So, we will get the corresponding spectral lines, and energy of the spectral lines are 2b, here 4b, here 6b, here 8b. That means, here I will get spectral lines, and spectral lines are equally spaced, okay, equispaced, and this difference between two spectral lines, this is 2b. So, from rigid rotator model we got the we will get the spectra, of diatomic molecule, okay, linear molecule, and it will give equispaced spectral lines, and difference between the successive spectral lines, that is 2b. Okay. So, next class I will continue discussion on this issue. Thank you.